Hello, what's up math learners? Welcome to our math learning with Sir Ash, and this is the topic that will be discussed on grade 7, quarter 1 in the first week of the curriculum school year 2020-2021. So, this topic is all about the set theory. The question is, what is a set theory? Set theory is the branch of mathematics that studies sets, which are collections of objects. Although any type of objects can be collected into a set, set theory is applied most often to objects that are relevant to mathematics. Now, sets are used to define the concepts of relations and functions. The study of geometry, sequences, probability, etc. requires the knowledge of sets. Studying sets will help us categorize information. It also allows us to make sense of a large amount of information by breaking it down into smaller groups. Now let's talk about the discussion about sets. By definition, a set is any collection of objects specified in such a way that we can determine whether a given object is or is not in the collection. In other words, a set is a collection of objects. These objects are called the elements or members of the set, and this is the symbol for our elements. Alright. Now, for example, if set A is equal to the list of members A, B, C, and D, then we can say that B is an element of A, which is also said as B is in A. But we cannot say F is an element of A because F is not an element of set A, or F is not in A. So the symbol for not an element is a symbol E with a slash sign. Alright, let's continue. The following points are noted while writing a set. Sets are usually denoted by capital letters like capital A, capital B, capital S, and etc. The elements or the members of a set are usually denoted by small letters such as A, B, T, U, and etc. Examples, we can use the name of the set as set A, and the elements are A, B, D, number 2, and number 4. Or we could also say another set, capital B, in which the members are math, religion, literature, and computer science. Now let's now go to how do we denote a set as an object. Where it is desirable to refer to a set as an indivisible entity, one typically denotes it by a single capital letter. By convention or convenience, particular symbols are reserved for the most important sets of numbers. So if we can see this kind of symbol, a 0 with a slash, that is called an empty set. If we use the capital letter C, it is usually denoted as to the complex numbers, while a capital N stands for the natural numbers. A capital Q refers to the rational numbers from the quotient, and capital R are considered to be real numbers. And finally, letter Z or capital Z refers to integers from the word Zahl, which is the German for integer. Now, how do we know that a set is well defined? A set is well defined if we are able to tell whether any particular object is an element of that set. Example, if set A is equal to X such that X is a winner of an Academy Award, then we can say that this is a well-defined set because we can list all the people who are the winners of an Academy Award. Now, if we consider another set, we have set T such that X is tall. Now, that is not a well-defined set because being tall is not well-defined. Alright? So, for the first set, we consider this as a set. But for the second set, this is not considered as a well-defined set. Okay? So, that is our difference between a well-defined set and a not defined set. Alright, now more examples. The set of former Nobel Prize winners. Now that is a well-defined set. The set of tall students in our university is not a well-defined set because you cannot consider what is the standard idea for considering a student to be tall. Alright? Now, I have said earlier that a set has elements or members. Now, elements is also a part of sets specifically because the elements are those things that are inside a set. Elements are those individual objects contained in a collection. So for example, we have X, A, P, and D. So those are elements or known as the members of the set. Note that each element of the set is written only once. So remember that the element will not repeat on a single set. In addition, the order of elements in a set is not important. So meaning, if you have written A as one of the members of the set, you can follow it with Z, then follow it with B, then follow it with M, then follow it with another letter, regardless of the alphabetical arrangement of the letters, as long as you are talking about the members of that specified set. So how do we represent sets? Well, there are two ways to represent sets. The first is by listing the elements, and the second is by using the set builder notation. Now, what are these types of representing sets? Now, let's talk about the set builder notation. The set builder notation is a way of showing sets in which you are giving description of the well-defined set. For example, the set C is equal to X such that X is a carnivorous animal. Now, as you can see here, the list of carnivorous animals are not given, but this kind of set talks about all animals that are carnivorous. Alright. Now, how do we read the set builder notation? So we have here B, set B is equal, or set B is the set of all X such that X is a season of the year. So note that we can use the symbol colon instead of the slash sign, or vice versa. So in using set builder notation, you just need to consider how to read them. Like set B, set is the set of all X such that X is the season of the year. Alright, now let's go to the listing method, the second way of representing sets. Listing method is very easy because what you will do is you just make a bracket and then list all the members or elements of that given set. So for instance, we have set C is equal to the list of elements such as I, you, he, she, we, and they. Another set is equal to the set of clubs, diamond, heart, and spades. So as long as all the list or all the members of the set are written, that is considered as the listing method. That is how we use this kind of representation for sets. Okay, now let's go to the types of sets. Now, we have a set that is known as the empty or null set. This kind of set contains no elements. So this is called an empty set or a null set. This is labeled by a symbol that has a 0 with a slash going through it. You can also use two brackets without anything on the middle of those brackets. Alright. So more emphasis of this empty set or null set is this example. Set A is all X such that X is a month containing 32 days. So as we all know, in our calendar, there are no months in the year that contains 32 days. So therefore, we will not have any elements for this given set. Okay, now let us go to another type of set. This is known as the universal set. The universal set is the set of all elements under consideration in a given discussion. It is often described by using the capital letter U. Alright, now for more emphasis, for instance, we have the universal set is equal to A, B, C, D, E, F, G, H, I, and J. Now, as we can see in this figure, we have set A as A, B, and C. We have set B as C, D, and E, and we have set C as F, H, G. However, there are two elements outside the sets A, B, and C, such as the I and J. In order to become a universal set, you must consider all the elements in those given sets, and even those elements outside those given sets. Alright? So that is how we consider the universal set. Now let's go to the cardinality of set. Now this part is not actually a type of set, but it is a very essential part of the sets. Now what is the cardinality of sets? The actual number of elements in a set is known as its cardinal number. It is described by using a small letter n with a quantity a, or n of a, as to be read. So now if you use this denotation n of a, you are considering what is the actual number or how many elements are there in that specified set. Another thing, we have finite and infinite numbers or sets. The set can either be finite or infinite depending on the whole number. If the set's cardinal number is a whole number, then it is finite. If it is not, then it is infinite. Now what does this mean? Actually, there are sets in which you can count them. As long as you can count them, that is considered as a finite set. But if it is infinite, like 1, 2, 3, and then an ellipsis, or 1, 2, 3, dot, 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 therefore, it will continue so on and so forth until the last number. But all we know that if it is an infinite number, therefore, we cannot consider it as a finite set. Instead, it is known as the infinite set. Alright. Now, here is more emphasis as the finite and infinite sets. The set of days of the week is considered a finite set because we all know that the set of days in a week are only 7. That is from Sunday to Saturday. Alright? However, the set of whole numbers is an infinite set because the whole numbers will start at 1 and then we don't know when it will end. Because if we consider counting, we will have all our days counting, but still, we still cannot finish counting. So that is an infinite set. Alright. Now, let's go to equal sets. Equal sets. There are sets that are equal. They are said to be equal if they have exactly the same elements. Example, if those elements are in A and another elements are also in B, then we can say that A and B are equal sets. Okay, for example, let's say set A has 1, 2, 3, and 4, while set B has also 1, 2, 3, and 4. So that is the time we can say that set A and set B are equal sets. Okay, so if A is equal to B, then A is also equivalent to B. Now, so this equivalent set is another description for sets. Okay, because equal sets and equivalent sets are not the same. We can only say that two sets are equivalent if the number of elements in A and the number of elements in B are the same. So that is how we describe about equivalent sets. So remember, if A is equal to B, then we can also say that A and B are equivalent. However, if A is equivalent to B, then A might not be equal to B. For example, if set A is 1, 2, 3, and 4, while set B is 5, 6, 7, and 8. Now, set A has 4 elements, while set B has 4 elements. So they are considered as equivalent elements, but they are not considered as equal elements because the elements in A are not the same as the elements in B. Okay, I hope you got that one, math learners. Now let's continue. We have also the subset. A subset would occur if every element of one set is also an element in another set. Using A and B, we could say that all the elements of A were also in B too. And it would be written as A, then a sideways U underlined with B after. Okay, more emphasis to that is this one. Okay, so set A is a subset of set B if every element of A is also an element of B. So, if A is a subset of B, that is how we denote it, a sideways U and then an underline below. So, this is read as A is a subset of B, or A is contained in B. Now, if this symbol is reversed, such that if B, this symbol is not known as the subset. Instead, this is known as the superset. Okay, so if B is a superset of A, then we can say that B is a superset of A, or B contains A. Now, let me emphasize this one. Subset and superset are almost the same depending on how you put the set first. So if the bigger set is put first than the smaller set, then you can use the superset. But if the bigger set is put second of the smaller set, then you use the subset. Okay, so as you can see in this figure, you can look at here. Now, as you can see here, A is inside of B. So A here is a subset of B, while B is the superset of A. However, we have here the universal set, which is the superset of all. Okay, so therefore, we can also say that A is a subset of U, B is a subset of U, and A is a subset of B. So these are the denotation. Now, let's have the properties for subset. Every set is a subset of itself. So A is a subset of A. The empty set is a subset of any set. So a null set is a subset of A. If A is a subset of B and B is a subset of A, then we can say that A is equal to B. Or that means that these sets are overlapping. Okay. If A is a subset of B and B is a subset of C, then we can say that A is a subset of C. So this is a consideration of a small set is inside a medium set, and this medium set is inside a bigger set. So we can say that a small set is also inside in the bigger set. So that is what we call as the transitive property. The number of subsets of a set with n elements is 2 to the power of n. Okay? So that is how we consider the number of sets. Okay, so we have here an example. Set A is all values of x such that x lives in Davao City, while set B are all values of x such that x lives in the Philippines. Now, the question is set A a subset of B? So for this example, our answer is yes, because Davao City lies within the Philippines. So A is a subset of B. Okay, we go to number 2. We have here set A as the list of members 1, 2, and 3, while set B are the numbers 1, 2, 3, 5, 6, and 7. Now, question, is A a subset of B? Now, as you can see, 1, 2, 3 is also a part of B. Therefore, we can say that this is yes, because A is a subset of B, because all the numbers in A are also in B. Now, let's go to number 3. If the set A has the list of members such as 1, 2, 3, and 4, while set B has the list 1, 2, 3, 5, 6, 7, and 8, is A a subset of B? So, in this kind of example, our answer is no, because as we can see in set A, we have 4 there as an element. However, in B, 4 is not a member of B. So, it is not included in set B. So, therefore, A is not a subset of B. Okay, I hope you got that, my dear math learners. Now, let's go to the relationship of sets. Now, we have here the union. The union of two sets would be wrote as A union of B, or AUB. So, that is how you denote it. But that is read as A union of B, which is the set of elements that are members of A or B, or both two. Okay. So, using the set builder notation, we can use A union of B is equal to all x such that x is a member of A or x is a member of B. So, remember, in this union, we tend to get all the members of one set to another members of another set. So, more emphasis of that relationship is this example. So, we have here two circles, two sets, in which A here has A, B, C, D, and E. While B here is A, C, F, G, and H. Alright, now if we consider what is the union of A and B, or A union of B, then we get all the members inside A and B. So we have A, B, C, D, E, F, G, and H. That is how we consider the union of sets. Okay, now let's go to the properties of the union. So let A, B, C be 3 sets. So we can say that the A union of A is also A. So that is the idempotent law. We also have, if the union of A and B is given, then it is equal to the B union of A. That is the commutative property. Now, here is another, if the union of A, B, and C are given, and then you consider first the union of B and C, then that is just the same as the union of A, B, and C, even if you consider first the union of A and B, known as the associative property. Now, we also have here the union of A and the null set is also equal to A. That is the identity law. And the A union of U is equal to U because U takes it all. So that is the properties of the union. Now, let us go to another relationship. This is known as the intersection. So the symbol for intersection is the reverse of the union. Okay. So intersection are written as A intersection of B is the set of elements that are in A and B. So earlier we said if we talk about union, that is A or B. So if you take A and B both at the same time, while in the intersection you just considered the same element, or what is the element that is both in A and in B. So we are considering the same element for the two sets. So using the set builder notation, it would look like this. A intersection of B is equal to all the values of X such that X is a member of X and X is a member of B. Okay, so the key word here is that in using intersection, we use the word and, while in the union, we use the word or. Okay, so if you take or as the word, then that is a union. Then, while if you take and as the word, that is the intersection. Okay, so more emphasis, we have here the given two sets, the set A and the set B. So if we are talking about intersection, we are just looking at the similar side in which and in where the A, set A and set B intersected. So as we can see, there are two elements here that are both in A and B. So A intersection of B are or is equal to 2 and 4. Okay, so that's it. 2 and 4 only in this given figure. Okay, now let's go to the properties of intersection. The A intersection of B is equal to A. That is the idempotent law. While A intersected to B, or the A intersection of B, is just equal to B intersection of A. That is also the commutative property. Same goes with the associative property, whether you consider first the intersection of B and C or the intersection of A and B. While the intersection of a set to a null set is the null set. Now, it's not the same as in the union, because in the union, if A union of null set, the answer is the set itself. But in the intersection of A and the null set, the answer is the null set, because you are finding what is not inside of that set. Okay, while the intersection of A and U, or the universal set, is equal to A only, because we will not consider all the other sets that is outside of A. So that is our properties in the intersection relationship about sets. Okay, so now let us go to the final relationship of sets. This is the complements. So with set A being a subset of the universal set U, the complement of A, this is the denotation for the complement of A, the name of the set with an apostrophe. So the complement of A is the set of the elements of U that are not the elements of A. So technically speaking, when we talk about complements, so it is those elements that are not inside or that are not a member of that set being talked about. So if we are talking complements of B, so we are talking about those elements not in B. So if we are talking about elements, the complement of A, those are elements not in the set of A. Okay, that's it. Now let us go to a more emphasis. So this is the figure, this is the diagram. So if this is our set A and this is our universal set, our complement here is outside of that set. Okay, so the complement of set A. Now let's talk about the properties. Let U, or the universal set, and A as a subset of U. So this is, or so these are the properties. A union of complement of A is equal to the universal set. The intersection of the complements of A is equal to a null set. Why? Because those things not in A and those things in A, they don't have any similar elements. Okay, the complement of U is equal to a null set. Now here is the double negation. Okay, the complement of A is equal to A. So this is the elements not in the element of A. So that is considerably A itself. Okay, now let's recap our discussion. We have the empty set as the null set, right? The finite set are those sets with a definite or a finite number of cardinality in a given set. So technically, finite set are those sets that we can count all the members. Infinite sets are those sets that we cannot count the members. Okay, so they are infinite. Equal sets are those sets that have the same elements in the sets. We also have the subset. The subset is a part of another set. Okay. And then we have the universal set that contains all the objects of those given sets. We also have the operations of sets known as the relationship of sets, the union, the intersection, and the complement. The union is the use of both elements. Okay, both the elements of two sets, or if two sets are given. Intersection of sets are those elements that are both in the same of the two sets. So these are the identical members of a two given set. Okay, while the complements of set is outside the given set. Okay, so those are the elements. Now I have also given you some figures, and for more emphasis, those figures are known as the Venn diagram. Now, Venn diagram is named after John Venn. Okay, it is a method of visualizing set using various shapes, and these diagrams consist of rectangles and circles. So as you can see here, the shaded region, this talks about the union of the sets, while the intersection is only the similarity of the sets, while the disjunction, you will learn about this one. This is the outside, the things that are not their intersection, and the subtraction of sets. So on the next discussion, I will be also going deeper on the operation about Venn diagrams in terms of sets. Okay, and other definition is the disjoint. So that is A intersection of B that is equal to 0. If the intersection has no same elements, so that is considered as a disjoint. Now the difference of sets is when a set is being subtracted to another set, and if ever there are elements that are left, that is known as the difference of the sets. Equivalent sets are those sets that in which their cardinality number are the same. And I hope you have learned so much about this introduction of set. This is your free access math teacher, Sir Ash. And always remember, it is fun to learn mathematics if we are together. Thank you and God bless.